Okay, good morning, class.
Morning, Doctor.
Okay,
Morning, Doctor.
yeah, so I would like to remind all that we have
Doctor.
a test tomorrow uh, uh, as being told in the WhatsApp group. Okay, so please make sure you attend the test. Okay, all right. So for today's lesson, we are going to continue with flexibility methods applied on beam structure. And for this class, we are going to have about 40 minutes on this explanation or exploration on example 3. And then we're going to the tutorial 6b. Okay, so let's start with this example 3. Please prepare your handout. Okay, the handout is from you can obtain from UFuture, and with these 7 pages, beam, the file name is beam examples, and we are going to look at these examples of these overhanging beams. Okay, CD. Okay, so this is a question. I I place it in a, PPT file. Okay, it is the same question. Okay, so let me share with you what if, okay, for flexibility method, what if the you have two redundants, okay, where your D is equal to 2. So we need to start with identifying the redundants. Okay, class, if you have any questions, just stop me, okay, during my explanation. Okay, whether I'm moving too fast or yeah, you can ask me to be skip some of the one that uh, you are very familiar with. Okay, so now D is equal to R minus N minus C. And in this case, we have fixed supports. We have AY, AX, and MA. Okay, we have BY, and we have CY. So altogether, this support reaction, we have 5 numbers. And we have always 3 for 2D system, and we do not have any hinge here. Okay, so therefore, this system have 2 redundants. Okay, so you need to remove your first redundant and decide for your second redundant. Okay, in this case, okay, it's given to you. The problem is to determine the moment A, okay, at for the beam. So you can decide or choose, okay, moment at A as your one of your redundant. Okay, so that when you solve for the redundant, you can directly solve for the questions. Okay, and then but it also requires to determine the remaining of the support reactions. Okay, so but so means that whenever you have choose, you have to also uh, putting in the real system and analyze for others remaining support reactions. So in this case, BC and CY has been chosen. Okay, meaning that R1 is BY and R2 is CY. Okay, so E is given to you, is constant for all the spans, and I is different, okay, between AB, BC, and CD. This is due to the different sizes, okay, of this section. Okay, so this is from the design where they might need a greater, okay, size, okay, in the bending resistance for AB, and then later BC and the lesser size for CD. Okay, so we can have a look on this primary system and also redundant system. So now the primary structure, we name it as M naught. Okay, from the feedback tutorial 6a, I understand that few of my students still do not aware on how many primary structure or how many redundant structure they need to draw. Okay, so I remind all again. Okay, we will always have one primary structure only. Okay, so M naught will be only one. The primary structure, one only. Okay, one numbers. Okay, and the redundant structure, you are going to have uh, 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 D numbers. Okay, I would say here D numbers. Okay, the redundant structure, you have D numbers. So if in this case we have D equal to 2, so you are going to have M1 and also M2. Okay, so now what is how to draw the primary structure and how to draw the redundant structure. So in primary structure, we need to remove all the redundant. Okay, all the redundants, meaning that in this case we have two redundants and we have chosen by and cy as redundant. So we remove all of these by and cy. So therefore, if you can see that by, cy has been taken real structure. And then you remember all these real loads, and this will be the primary structure. Then how about M1 and M2? So M1 and M2, the geometry and the support conditions are the same. Okay, because they are taken from primary system. Okay, if you can see that by, okay, no support reaction, cy, no support reaction. Okay, similarly for M2 and by and cy. Okay, and then the treatment is we need to remove all the real loads. So the difference from primary structure is there are no real loads at all, okay, in this redundant system. So therefore 20 kilonewton, 5 kilonewton per meter is not, okay, are not in your redundant structure. And then you need to apply, okay, here, or I've write here. You need to apply the redundant of number 1 with 1 unit force. So now you have taken out by vertically, so you apply back 1 unit force vertically, 1 kilonewton at by. So now you are putting by equal to 1 kilonewton. Okay, but that is not your support, it's a virtual load. And then for M2, you place back cy equal to 1 kilonewton. So in each of these redundant structure, you apply only one, okay, virtual load, okay, 1 unit force of the virtual load at the redundant location. Okay, so this is how you plan for, draw for your primary redundant structures. Then we're going to decide on the sections. Okay, I have seen and give feedback, okay, on your tutorial 6A, and I hope all of you has understand how to choose, okay, a way to cut the section. Remember, if it is in a span, okay, we need to cut at least one section. Like for example, AB, we cut one section. B to C, another span, we need to cut one section. C to D, we need to cut at least one. And then you observe, okay, if there is any differential in terms of loading, like for example, in span BC, you have this 20 kilonewton acting at E. Therefore, you're going to cut a section before and after that point loads. Okay, and you are going to always cut one, okay, for your UDL. Okay, either it is a rectangular or triangular. Okay, so you're going to cut one. Okay, of course this UDL must have the same slope. Okay, if for example at CD, okay, you have this shape. Okay, so you need to cut how many section, class? Trapezoidal.
3.
3.
Yes, 3, because the slopes are different for this UDL. You need to consider this. Okay, this is your first UDL, first type of UDL. This is your second type of UDL. And this will be the third type of UDL. So you need to cut this 3 section. Okay, so and what if, okay, like for example, CD, okay, you have this UDL, and you have one more point load acting, okay, somewhere in the within the CD. Okay, so how many cut section you need to provide?
2.
Two, thank you. You know that in the one slope of this UDL, you need to provide one, but there is one point load acting at the, within CD, so you need to cut also. The bending functions will be different, okay, before and after the point load. Okay, so I have also set 3 rules for you to follow. Okay, if you I would like to remind all again, okay, on this 3 rule for this flexibility method. Okay, the first one, this is a bit messy now. Let me erase my board. Okay, I will put it somewhere here. Okay, so the first rule is make sure the numbers, okay, of the section and their range are the same. Okay, same for all these M0 and M1. So now you have 4 cut sections for M0. You will have 4 cut sections for M1 and M2, and they must be having the same range. Okay. Then number 2, consider same section, same side of section. Okay, meaning that if you are considering right or left, okay, so you do so. Okay, the same for M0 and also M1. Or easy way to say, your X, your starting X, okay, is the same. Okay, same for both. Okay, system M0 and M1. Starting, okay, starting of X. Okay, number 3 is your sign. Okay, for the moments M0 and M1. Okay, must be the same. If you are taking a positive sign here, okay, make sure you are doing the same, okay, for all these cut section. Okay, so there are 3 rules to follow. Okay, then because we want to multiply the moments in between these systems. Okay, so don't get it confused later. Okay, so we make sure we comply these 3 rules. So okay, so I would like to explain on the, maybe I'll create one, okay, just for this, crop it. Okay, so that I can have bigger, maybe have a bigger. See, the most bigger is like this. Okay. Okay, so I would like to explain when you're dealing with these triangular loads. Okay, first of all, okay, for this cut section number 1, okay, in order for us to know what is the load acting and giving the moments to cut section 1, we need to know the height of the loads here. Okay, we know that at, sorry, I don't know the 4 meter, 1.5, 1.53, 4 meter, 1.5 meter, 1.5 meter, and then 3 meter. Okay. So we know that at 4 meter the height is 5 kilonewton per meter, but we do not know, okay, at this specific X distance from D, what is the height of the triangular loads. Okay, then you can practice by this geometry or ratio of these 2 triangle. Okay, you can just simply state that the height of this that you want to find, okay, is y. Okay, there are two triangles. If you can see that, the small triangle where you have a width of x and the height of y. Okay, if we extend it, the bigger triangle, okay, where we have the width of 4 meter, okay, we have the height of 5 kilonewton per meter. Okay, so you can name this 4 meter as big X, and this 5 kilonewton per meter is big Y. Okay, just write and easy equations, okay, to look at this relationship between the small x and the big X. So you just write, because we intend to find the Y, so you can put Y first, Y over X, okay, and then big Y over X. Okay, so now we want to know the y, right? Small y. So just solve for this equation. So it will be y, big X, and the x. So now you know that big Y is 5, right? And X is 4, right? So you know that the height of this triangular lots is actually 5 over 4x. Are you clear, class?
Yes.
Yes, yes.
Okay, so I'm explaining now how to determine the height, okay, of this triangular lot at any way within this CD. Okay, if you have a specific value for x, you just substitute it into this. Substitute it into this equation, you determine the height, okay, of the triangular lot value. Okay, so now I would like to erase this to explain on how to get the moment at the cut section. Okay. So now you already know how to get this 5 over 4 x. Okay, here. Okay, so you know that this is, okay, 5 over 4. Can't see well, so 5 over 4x. Okay, so now I would like to take moments here for cut section 1, 1. So I refer to my right section, okay, where I start my x from D. Okay, so now I will have only one these triangular lots with a height of 5 over 4x. So I can just represent it by a point lot here. How to get the lots? By taking the area of this triangular lot, triangle. So it will be half multiply the base x, and the height of the lots is 5 over 4x. Okay, so this will be your point lot. Okay, so but now you need to know the distance, okay, in order to get the moments. Okay, what is this distance? Anyone know? The distance of this point lot, the resultant to this cut section.
1 over 3.
Yes, 1/3. Okay, please remember, okay, the centroid, the lots will be acting at the centroid. The centroid is always close, okay, to the highest highest value of this triangle. Okay, therefore this must be 1/3 of the L, and this must be 2/3 of the L. Oops. So it depends on where you want to take moment, either taking moment to this P, let's say, or taking moment about Q. So it depends. Okay, but now we are going to take a moment about this cut section 1, 1. So now this is 1/3 of x. So I'm going to write it here, x over 3. Okay, so to get my moment M, so I don't have space here, I will just write here, will be equal to the lot. The lot is half x and 5 over 4x. You can simplify it later. And the distance will be x over 3. And then you check on this sign of this moment. The lots, the moment, applied moment is acting the same direction with your internal moment. Okay, so it will be negative sign. So this is your moments. You can simplify it later. So this is multiply. Can I put it here so that you won't confuse with x? Okay. So then I would like to move to cut section for my M1. Okay, I found that from the right section, there are no loading at all. So I put a 0. Okay, quickly for my moments. Are you clear, class? Do you have any question for me?
No.
Okay,
Clear,
so I would like to proceed with card section number 2. So now I've moved to number 2. Okay, this is also 2 and then 2. So I also consider the right, okay, right section. Okay, so once I considering for M0, my M0, I found that I have only one triangular load. Okay, the one that you have calculated just now, you can just, yeah, you are not going to use it anymore because you already have a different X. The X now is from, can I erase this board? Have you take down the notes, necessary notes? Can I erase this?
Yes,
Yeah, yes.
can.
I worry that my explanation you will confuse. I will make sure it is cleaned. Okay, so now I'm looking at this number 2. Okay, and my X now is from D to my cut section. This is the X, and I have loads, triangle loads with this 5 kilonewton per meter height. Okay, so I need to find my resultants. Okay, which acting at the centroid. Okay, which is acting 1/3. Okay, of the base. The base is 4 meter just now, right? So this will be the base is 4 meter. So this will be 4/3, the distance. And to get the point load here, okay, represent this triangle loads to point load, it will be the area, half of the base, and multiply with the height. Okay, so this will be your necessary inputs. Okay, but we want this, right? We want this. We want this distance. Okay, it's not this 4/3. We want this distance. Okay, how much is that distance? So we need to know how much is this, right? So it will be 2/3 of the 4. So or 8/3. Okay, so you need to in order to get this distance, you just minus from X minus with this value, right? So you get X minus 8/3 for the distance. So to get this moment, I write here. So the moment will be the loads. Okay, you can simplify that later. And the distance, X minus 8/3. Then you check again on this sign. Okay, the applied moments and the internal moment is having the same sign. So you can just give it a negative. So you get the moments here. Okay, so I go directly to 2. There is no, okay, loading. I put it at 0. And then okay, so for my M2, so for this I have one loading which is at CY 1 kilonewton, and I need to know what is the distance of this one. Do you know this distance? This is 4 meter. Class, do you know this distance?
X minus 4.
Yeah, thank you. X minus 4. So your moments here will be the loading multiply with the distance about the cut section. And if you check this applied moment and also the internal moment, they are opposite, in the opposite way. So you give a positive sign, okay, to these moments. Okay, so this is how you determine these moments. Do you want me to continue with the section 3.3 and 4.4? Class?
No.
Tujuh, doktor.
Okay, so I believe because my intentions today to share with you is dealing with this triangular load. So I think the remaining here you can try on. Okay, there should be yeah, the skills should be just that I shared just now should be able to perform for the 3 and 4. Okay, so once you have obtained all these moments, okay, you can put it either in this tabular form, or you can directly put it in the compatibility equation. Okay, so if you are worried that there is just too messy in your calculation, so you put it in the table. Okay, so make sure these sections must be correctly, okay, I mean the range, okay, must be correctly input, because this will be used, okay, in your compatibility equation later. So M0 is from primary structure, M1, M2 is from the redundant structure. So you need to also be aware that in this problem, the EI is different. Okay, now we have four cut section, DC, CE, EB, BA, right? But in this, we have AB, BC, CD, meaning that in this BC, this is spanning BC. Okay, so the EI applied BC here, and this is for DC, EI DC, and this is for the EI BA. Okay, so let's have a look on this, maybe how to do this. Okay, I'm going to copy the table so that okay, we're going to see how this information in the table can be put in the compatibility equations. Okay, so maybe it's quite small, okay, for the table. Okay, so we just try to randomly select, okay, to understand. So in this, you need to be able to write this compatibility equation. When D equal to 2, you need to write delta 1 equal to delta 1 naught plus delta 1 1 R1 plus delta 1 2 R2. Okay, this is your first equation, and you are going to have two equations at total, where you have delta 2 naught plus delta 2 1 R1 plus delta 2 2 R2. Okay, and this R delta 1 2 and delta 2 1 is actually is the same value, so you no need to calculate twice. Okay, so let's have a look on this delta 1 1. What you need to input? 1 1 means that M1 multiply M1. So just go to M1, column of M1, and see there is no input from DC, section DC 0, section CE 0, section EB 0. So you only have inputs from BA. So this is from BA. Okay, so BA, okay, look at the BA, EIBA is 12,000. So you can put it in the your equations for EI. And then the range is from 7 to 10. Okay, 7 to 10. So you can get your delta 1 1. Okay, but for delta 1 2 or 2 1, okay, oh, still you are multiplying M1 and M2, so you will not have any result for DC, CE, EB, because they are all 0 moments, and you are referring to BA as well. Okay, so similarly, the range applied, EI applied, and just take this is M1, this is M2. Okay, so delta 2 2 will be referring to M2 columns only. Okay, where you multiply twice M2, and you found that you have why there are three inputs here? Why these are 2 only? Do you notice that? This is because this CE and EB, they are actually if CE, EB, and BA, they are having the same EI, you only need to write to one equation. Okay, because the moments are the same. For these 3 sections, you just need to name the range from 4 to 10. That's all. Okay, but now your EI is different in this case. For CE and EB, you fall under BC. you fall under span BC where your EI is 10. Okay, so this statement is for CE and EB. Okay, and for member CD, sorry, it's not CD. Member AB, okay, I'm looking at this. Member AB, the EI is 12, okay, 1,000. So you have 12,000 stated here. So this statement is for BA. Okay, so the range CE and EB has been combined, okay, from 4 to 7, okay, because they are sharing the same moments. If they are not the same, then you cannot combine this integration. Okay, so you can find this delta 22 as well. So this delta 11, 12, 21, 22, if written in the matrix form, we call this a flexibility matrix. Okay, you need to aware of these terms. Okay, sometimes because the process is just too long, okay, maybe it will ask you just to determine the flexibility matrix. So you need to place it in the matrix form. Okay, any questions, class? Up to here?
No, Doctor.
No, Doctor.
Okay. Thank you for your feedback. So I'm going to next slide. Okay. So this is just a repetitive process. I'm not going to explain the details here. So, but you need to obtain the delta 1 naught, delta 2 naught, okay, from this equation, how to get delta 1 naught and how to get delta 2 naught, okay. So once you have solved for this delta, you can put it in a matrix form, okay, to solve for your redundance. Remember, your redundant 1 is actually your BY, your redundant 2 is your CY, okay, and you get a positive value here. Positive means that your sign, your assumed sign, okay, is correct lah, okay, or your real structure, the BY and CY is acting exactly like what you have assumed. Okay, of course you can use this simultaneous equation, two equation to solve your R1 and R2. Okay, so to solve your problem A, it said that you need to determine all the support reaction, how you need to do that. So you need to put in the real value from your calculation R1 and R2 into the real system. Then now your system become it is still indeterminate, but some of the redundant forces has been solved. So you can just use your skill of equilibrium equation, summation moment. Okay, taking summation moment MA equal to 0, you get MA. Taking summation Fy equal to 0, you get AY, and summation Fx equal to 0, you get Fx. Okay, AX. Okay, so these are how you analyze and solve for A. Okay, but we have one more question to share. What if you need to determine the displacement of this indeterminate system? Okay, so of course you need to solve for A first. Okay, you need to solve for A. Okay, to solve for the redundant forces in the indeterminate system before you can move to determine the displacement. So this is the question 2 is not about flexibility method. It is about your virtual work method. So maybe I can explain on this rotation at B. Okay, rotation at B means that you are talking about rotational displacement. So meaning that your applied virtual load, okay, your virtual load must be in 1 kilonewton meter in terms of moment. Okay, many students do not put a correct units. Okay, so now I remind all of you that for a moment the unit is kilonewton meter. Of course, you can use Newton meter and so on, but you shall not forget about this meter. Okay, because it's load multiplied distance. Okay, so we are going to apply at the point of interest, which is at B. Okay, you can put the assumption either this is clockwise or counterclockwise. Okay, you apply it at B. Now we need to also cut 4 sections actually. Okay, so but by observation, you know that 2 sections is sufficient. So even though you cut another one here, you still get the same answer. Okay, with this, and if you still cut one more section, you get the same. Okay, with this. Okay, so but when we place in this table, you will see that this column is from real structure. It is not from your primary structure. Okay, this is from your real structure. How to get this real structure? Moments. Anyone? How to get the M for the real structure? Want to try? Oops. So the moment for the real structure means that after you obtain this by and cy, you need to cut section again and get these moments. Okay, and these moments are all from real structure, not from your primary structure, not from your virtual structure. Okay, so it's M, but why this is NIL? No need to find. Is that DC? No value. There is a value, right? They must have a value. Okay, but we can skip it because we know that M is going to multiply with small m later. If the small m, there is no value for small m, so the big M, after you apply also, they will be not used. Okay, so it's just skip it. Okay, this is actually has value, but owing to this zero here, so it just skip the process. Okay, so now looking at once you have formed this delta B, the small m. Okay, so this is the equation for virtual work method. Okay, virtual work equation. The small m is from this virtual structure, and the big M is from real. This is from real. This is from your virtual structure. Okay, not redundant structure in your flexibility. Yeah, nothing about that. Okay, so then you apply appropriate EI. Okay, then you get the value, and the value is positive, meaning that the direction, that you have assumed is correct, and the unit for this rotation is radian. Okay, class. Do you have any question for me?
No, doctor.
Yeah, then I end my explanation this morning. Okay, and I would like to give an instruction or tell you on how to proceed on the tutorial. Okay, session after I take your attendance. Okay, I will stop recording right now, and okay, and I will go to the UFuture to look at your okay. Wait, I need to remind myself where I stopped. Okay, so I go to online class. I go to active. Go to this. Okay. So, oops, you have already take your attendance. 10 for this. Oh, done. All right. So let me give you what you need to do. Okay, yesterday I will consider we failed to finish our tutorial. Okay, because I do not know what happened. Okay, but I hope today we'll have successfully giving you some feedback. Okay, let me quickly, maybe you need more time for that. So let me getting faster. Where is my tutorial? Okay, so now this is tutorial 6A. We already give feedback. So now I'm going to give an instruction for 6B. Okay, actually there is no need to have so much instruction here. Okay, but I'm going to I need you to maybe I will be the one who choose. Okay, either B or C. Today we are going to do either B or C. Okay, yeah, now you can choose. Which one you want to solve? B or C?
B.
B.
B. Okay, fine. We're going to solve for B. Okay, so what you need to do is you need to in this, I'm going to get feedback. I mean your answer step by step. Okay, the primary structure and redundant structure will follow whatever in your feedback last lesson, which is yesterday. Okay, so everyone follow that primary structure and redundant structure to start on analyzing. So the first one, I will ask for M naught. Okay, once you are ready, you send me the M naught. And the second one is M1. Okay, so and the third one is M2. Okay, then I want to see in the table form, okay, of the all these compatibility equation inputs. Okay, then I want you to write the compatibility equation. And lastly, compatibility equation. Okay, and then lastly, I want you to solve for the there's no need to have so many steps here. Compatibility equation and the redundant solution. I think, yeah, I think that's all what we want to do. EI is constant. Okay, what else? It asks to find all the support reactions, right? And draw the shear moment diagram. If we can, we move to that. If not, then we were going to at least determine the remaining my house is very noisy. Okay, are you clear, class? First, I'm going to get the solution from you regarding M naught. Okay, don't snap me so many things, just M naught. Then I will ask for M1. Then I will ask for M2. Then I will see your table form to check your range. And then I will see your compatibility equation correct or not. Then I will see your how you determine the remaining reaction. Clear? So maybe I have 1A and 1B. I want to have more frequent get in touch with you. Okay, for M naught, so different students will give me this their result. Okay, so M naught will be the, I want to put it 1A for the support reaction. Once you get the reaction, you show me. Okay, then I move to 1B. You have more confidence of continuing. And 1B will be on the moment function. Okay, similarly to A also reaction, to B function, 3A reaction, 3B function. I will share with you with this in the WhatsApp group later. Okay, class, are you clear? If you are clear, then you move. Okay, for your tutorial.
Okay, doctor.
Okay, for those who want to ask question, you may stay. Yeah, I will be waiting. But this is just too noisy. Okay, so I see you tomorrow. But now I'm getting you in touch with in the WhatsApp group. Okay.
Okay, doctor.
Okay, doctor. Thank you.
Doctor, what
Yes.
is that? What is that? 2L?
2I.
2
2I is yeah. When you want to use the compatibility equation, you write integration over EI, right?
Yes.
Yes. So for this section AB, there is I only, one I. And for this BC means that they're double of the double size of this AB.
Oh, okay.
Okay.
Okay. Thank you, doctor.
Oh, shoot. I still with Lenny. Yes, you have want me to ask me something, Damia? Oops, they're just noisy. Aini, you want to ask me something?
For now, not yet, doctor.
Okay. So Husna, you want to ask me something? Nabila?
Doktor,
Yes.
yang tutor 6 ni kena submit dekat Teams ke?
Maaf Nabila, you kena kuatkan sikit sebab sini saya sangat bising.
Yang tutorial 6 ni kena submit dekat Teams ke?
Submit dekat Teams ke? Tak ada, saya cuma try macam mana nak guna assignment dekat Teams. Tapi saya tak tahu you orang get notify ke?
Dapat.
Dekat email ke apa?
Dia saya ada Teams dekat phone, lepas tu dia masuk kat noti dekat Teams.
Oh, jadi dia bukan send email lah. Sebab saya nampak ada yang view, ada yang tak view. Saya rasa you orang being notified. But just ignore that. Okay? Because this saya cuba-cuba.
Okay.
Okay.
So tak ada pun lah kena submit yang due dia malam ni.
Tak ada. Jangan risau.
Okay.
Okay, so nanti saya text semua orang, jangan bagi dia risau pula. Okay?
Okay. Thank you.
Okay.